Okay, so today we finally dive into the realm of true AR glasses, true augmented reality glasses, with the INMO Go. This is INMO's first generation AR glasses, monochrome green. They've since released the INMO Airs, a variety of polychrome options. I think they're on Air 3 now, which I believe use OLED microdisplays to inject light into their diffractive waveguides. But for this one, INMO claims a microLED light projector. So we'll take a look at that when we get further in, because many of the companies that are betting on true AR are betting on microLED as the technology to actually give us sufficient brightness for using these types of glasses in outdoor situations. So the INMO Airs, as you can see here, are true standalone AR glasses. We do not have a tether that we have to plug in directly into a PC or a phone. So this is one of the big advantages that we have for glasses like these. We can have true information displayed directly to our eye without actually having been physically tethered to our compute device. That's really where the advantages of these types of designs end and all of the drawbacks begin. So obviously, number one is going to be the color fidelity. Now, we won't judge INMO's design too harshly here because we are using a monochrome panel and you know what you're buying up front, but we do only have a green display that is projected to the user's eye through the waveguide element. And so for any color content that is required, you will not be able to see that in this particular display. This is primarily for text and other low data density information to be displayed directly to your eye in a heads-up display. We also have only a monocular display. Only the right eye has a display element. All of this information is projected through the waveguide and delivered to your eye. But as you can see, as we are scrolling back through various applications, there is a massive amount of light leakage opposite to the user as well into the world. And so if I move my head slightly, you'll be able to see all of the information as it's coming up through the heads-up display projected into the camera as well. Obviously, one of the main drawbacks of these types of diffractive waveguides that do not have any exit light control. There are some glasses in the works, especially from Meta and some other bigger brands with more advanced waveguide designs. But as a first generation device from INMO, one of the big drawbacks is generally all the information that's displayed to your eye is also projected to the world. Overall, we have a very old type of display, a VGA type of display, 640 by 480p resolution. This isn't a deal breaker, certainly. I would say that's enough for the text-based applications that INMO is trying to market as the principal use of these types of glasses. However, one of the most important things is the location of the exit grating. In our diffractive waveguides, the exit grating is the part of the waveguide that actually projects the image that has been magnified through the magnification gratings to the eye. And as you can see, it's not perfectly invisible inside of the waveguide. There is a exit grating on the top half of the right lens. This is, I would say, the most challenging aspect of the waveguide, because for a normal eye box and what I would consider a normal positioning of these glasses, really only the top half of that 640 by 480p, so only about 240 vertical pixels are visible at any one given time. You have to really move the glasses into a relatively awkward position, at least for my facial features, further down on the nose to be able to get the full screen. And even then, we have very limited screen capabilities. Now, one nice thing is that INMO quotes about 2,000 nits delivered to the user's eye. Even in a bright application like this, it's good enough where you have sun coming into the office. You're able to still read, if you focus on the text that's being projected to your eye, relatively well. But INMO has also given the user a magnetic attachment that helps decrease the overall ambient light, the amount of light that's coming in from the world side, and gives you a much nicer contrast. So with maybe about 40% transmission loss through these through this magnetic filter, we have a much better contrast for the display quality that is being given in this particular device. The battery life is fine. INMO quotes a 220 milliamp hour battery. We'll take a look at that later, but especially for green monochrome applications, this is quite good. At 100% charge, you'll easily get a full day of application use, as long as you don't have constant information delivered to your eye. By far, though, the biggest weakness for INMO is the software. The software experience has been awful, and INMO is really only a mainland China brand right now. Their push in North America hasn't really begun in earnest, even though they have an international site and start supporting many different global languages. But actually pairing these glasses to any of the latest iOS or Android devices has been incredibly difficult. So much so that the only way that I've been able to even pair these glasses to a device is by using an iPad, not even my Android or iOS phone. This is not a great user experience, especially since the apps require you to have the device in near proximity for the onboard processing required for things like automatic translation or AI agent chats. All of that is done on your device. And so if I have to have a separate device from my phone, which is the main selling point of these devices that you will be pairing to your phone or to your laptop, it is an automatic no-go. So the software experience is really leaving a lot to be desired. Software challenges notwithstanding, we'll go into the INMO Airs a little bit later on and take a look at the light engine that is housed here at the very front part of the right temple, injecting into our waveguide, into our diffractive waveguide, that is then delivering that up to 2000 nits directly to the user's eye. We'll also take a look at some rough temperatures that you can expect, especially on the right temple, where I suspect a lot of the processing is being done. But this is not likely to be running quite as hot as any of the OLED microdisplays in our display glasses, like the X-Reals, the Rokids, the Vitures. This is a much lower power consumption device, but we'll take a look and see if we can measure that as well. Since we're not tethered, it's going to be quite a different involvement. One of the nice parts about the INMO design is that they've used very little glue along the seams that protect the outside of our temples. So with just a little bit of isopropyl application along the seams on both ends, we can take a spudger and pry open, and then we're able to open up the right temple to see the circuitry on the right side of the INMO Go's, where we have the connector to the main board from the display module as well. That's in the right front stem, as well as the battery on the far ends of these glasses. If we zoom in, we can see that we have a 0.42 watt-hour battery, one on both sides, 110 milliamp hours, for a total of 220 milliamp hours across the entire device. Next, we'll have to disconnect the hinge mechanism that connects the front of the glasses to the right stem and see if we can separate the projector cleanly by removing the two Phillips head screws that we have on this right temple, as well as popping the connector for the display module away from the main logic board. We're able to remove the right stem completely and get it out of the way for the rest of our teardown. We'll take a look at this a little bit later on the blog, especially the battery and other components that are on this right stem, as well as the touch module that we see on the outside of the right stem. There's a small connector here that we disconnected during the disassembly of this right stem, where you actually have the ability to swipe on the stem and register that as an input. Really nice addition for the user experience. Now, to get access to the rest of the optical module, including the display projector and the waveguide, we'll have to take apart the hinge and remove the plastic components that are surrounding these display and lens optics, using again the same isopropyl and spudger method that we've used before. The hinge is held in place by 2 Phillips head screws, one on bottom and one on top. Once these are removed, we can take off the hinge mechanism and have access to the plastic plate that we will need to pry off of the display module very carefully. This metal part of the hinge is glued in tight to the body of the nose bridge. And unfortunately, while trying to remove this, the waveguide structure inside, which is a very delicate piece of glass typically with the nano-replicated structures that give us the diffractive waveguide element, has cracked. While we can still see a little bit of light ultimately going to the exit pupil, now we have significantly lower light efficiency through the glasses, as this crack is now the primary path for the light injection engine to exit to the user's eye. It's unfortunate to see such strong glue being applied to the components in the INMO Go, because this waveguide is very delicate and may have to be replaced just during normal wear and tear of this device. So in the future, it would be really great to see a more user accessible waveguide for all of these true AR glasses. Only with a lot of force and alcohol application are we able to finally get into this portion of the display assembly. Here we can see the ribbon connector that runs from the right temple all the way to the display projector. And if we pop off the ribbon connector here, we can see where we ultimately have our display module underneath. We also see that we have 2 Phillips head screws holding this part of the hinge to the main assembly, meaning that the only way to access all of the circuitry that we have in the smart glasses is by removing this incredibly stiff glue that INMO has used along the outer edges of all of the plastic pieces external to the device. That's unfortunate to see, because that will mean we will have, at the very least, significant cosmetic damage, if not potentially catastrophic damage, like what we see here with the waveguide. Removing these 2 Phillips head screws allows us to ultimately then take off this part of the hinge, leaving behind just the faceplate with the ribbon connector to our display cable. And what I will assume is a very long flex cable that runs down the entire front of the nose bridge back to the left temple to connect the batteries and the rest of the circuitry to the main logic board that we have with the USB-C charger. Much to my surprise, despite the side of these glasses being held in place with such strong glue, the actual front of the nose bridge is only held together by a few retaining clips on both the top and bottoms of each of the lenses, and a small amount of glue on the left and the right side. So using just a little bit of alcohol and prying force, we can very easily remove this component from the faceplate. And what we'll have left here is actually a very difficult assembly to ultimately work with, because we are now left behind with the display and waveguide on the left here, connected by a single very thin cable all the way to the left temple. So we'll have to be very careful when we disassemble this to make sure that we do not sever this cable, or else we will never get the signal back from the main logic board on the left temple. Once we've removed this faceplate from the main glasses, we can now start seeing what the waveguide and projector combination looks like here in the right eye. Zooming in, you'll be able to see a circular area which is called the input grating, and where the actual display projects the image first into the waveguide. Now, while the nanoscale structures that we have across our waveguide are not going to be very visible to the eye, on a macro size, we can actually see the resulting diffraction by the slightly hazier portion of the lens here. And this is known as the exit grating of our waveguide. The input grating takes the light from the light injection engine that we'll take a look at later, magnifies it across a magnification grating, and then ultimately delivers it to the user's eye in this exit grating, all using nanoscale features to diffract the light away from the in-plane direction that it has been magnified in, out of plane towards the user's eye, and unfortunately also out of plane towards the world, in this case towards the camera. After some very heavy-handed application of alcohol and a good bit of brute force, we're able to finally take the left temple cover off of the front side here, and then ultimately extract out the light projector and waveguide combination, the optical engine that actually drives the INMO Go's here. You'll notice that we also have one very long flex cable that is connected all the way from the left stem to the right stem. And this is explicitly just delivering power and data over to our optical engine. If we flip this over and zoom in for a closer look, we can see this flat panel cable is not actually connected directly into the display module. That is done via another connector that we have here on the bottom side of our display. If we zoom in a little bit more, we can see that the Pico projector is made up of a single small flat panel display that has been bonded directly to this optical housing. This housing determines the distance from the panel to the input grating that we saw on our waveguide and is a critical component of the overall optical path that a waveguide Pico projector like the one we have here has to make. So we'll remove this Pico projector from this barrel or this optical housing and take a look at the individual panel itself. This will have to be done by attacking the glue that holds it in place along the barrel, as well as removing the flex cable that has been bonded to the optical housing. Now that we've removed the small glue seam on either side of the Pico projector, we can then easily slide this Pico projector out of our barrel assembly, revealing just the input grating from the top, as well as what our display module looks like in these AR glasses. If we take a look at this Pico projector, essentially what we've got is a single monochrome green microLED panel on the backside connected to a lens barrel that helps project the image and magnify it before it enters the input pupil grating on our waveguide. This microLED module is adhered to the backside using a bead of glue on the backside of this barrel housing, and with a little bit of alcohol we can actually then disassemble this panel from the barrel, leaving behind just the individual microLED. On the other side, we now have our lens element to magnify the image. So our display module consists for these AR glasses of a microLED panel and its flex cable, as well as the lens array used to magnify that image. Now we can plug in just the microLED panel itself back into the circuitry and turn on the unit again to see if we can see the microLED image that is actually generated at the panel before this gets magnified and sent into the waveguide. Again, we only have 640 by 480 pixels in a roughly 0.1 inch display, as you can see relative to these tweezers. So we have a very, very small display for this particular application. And the power that these lenses allow us to get are what is able to deliver such a very large image into our field of view when the waveguide is coupled with this pico projector. These tiny pico projectors are made up of a microLED panel, like the one that we see here on the left, and a lens assembly that helps magnify the image coming out of this incredibly small 0.1 inch display, and takes those 640 by 480 pixels and ultimately inputs them into the input grading of our waveguide. This display is likely a Jadebird JBD Hummingbird Mini 1 microLED monochrome projector, where both the display and the lens barrel have been made by the display manufacturer and sent directly for integration with the customer's waveguide. This Jadebird monochrome green microLED panel is incredibly power efficient, allowing for the battery-driven form factor that we see here. This display is rated at running full operation at 60 milliwatts, almost 1/10 of the power that we saw from the micro OLED displays in the display glasses like we saw in Rokid, Future, Rayneo, and X-Real. And again, this is because of the very highly efficient micro LED technology that we're using here, but also because we are using just green, one single color, compared to the polychrome that has to drive 3 separate pixels in the OLED micro displays that we were looking at earlier. Jadebird Display rates these green micro LED panels at having a maximum brightness of up to 5 million nits. It's very bright, but this means that we have a very, very high amount of optical loss through a diffractive waveguide, up to or even more than 99% of the overall light that goes into the waveguide that we can see slightly at the bottom of this video now will get lost along the diffractive path that we follow with that projector. Again, that's why we need such high brightness micro LED displays where we will be able to accept 99% of loss, because even with that dramatic reduction in light, more than 1,000 nits, and typically 2,000 or more, will be delivered to the user's eye using these exit gratings in our waveguide. Micro LED also allows us to have a very wide refresh rate capability intrinsic to this particular panel technology. Jadebird quotes between 30 and 480 Hertz natively capable on the display panels. And again, this is going to depend specifically on the driver chip that brands like INMO or other glass manufacturers will choose to use. Overall, the panels are quite light at only 0.2 grams. This means that the display panel itself is a relatively trivial component for adding weight to the overall device. And what we really need to consider is the battery and other components outside of this display. Another area where we'll have a large amount of weight added is the actual waveguide itself. The waveguides that we see here at the very bottom are typically of a high refractive index glass material. And this glass will be very heavy compared to the plastic that's used. However, the waveguide itself is relatively thin. And so overall, the total optical module, which includes our display, our magnifying lens, and then our waveguide, is a very small portion of the overall weight of a pair of AR smart glasses. Where we need to really consider optimizations are all the other components to make a full system. But in this case, the display solution is quite well optimized, if not ideal, given the monochrome low 640 by 480p resolution that we're working with. The overall optical module, once broken down for a pair of these INMO Go glasses, is quite simple. We have our JBD microLED green projector on the far right, where the light from this projector is then magnified using our lens system that is directly glued on top of our panel. This lens system then injects the light into the input grating of our waveguide, which is contained inside of the barrel that we see here. And this grating serves to expand the light even further and magnify it before reaching the diffractive elements that we see on the far left of this waveguide. The diffractive elements are nanoscale features, typically lines or pillars, that help push the light from the in-plane direction that it has been bouncing inside of our waveguide to the out-of-plane direction directly to the user's eye, as well as out of plane in the opposite direction into the world side. This is a very inefficient method of taking our light from our display to the user's eye, and that's why diffractive waveguides typically have very high losses on the order of 99%. And so we need a panel that is as bright as these rated 5 million nit monochrome green LED displays to ultimately be able to deliver high brightness to the user's eye, something on the order of 5,000 nits, or as INMO quotes here, 2,000 nits, that is still readable even though you have a lot of ambient light coming in through these very transparent glasses. And this will be further helped by the addition of slightly opaque covers, where we can now get an even better contrast for that 2000 nits that INMO quotes to us. Overall, a really interesting first consumer product with both microLED technology and waveguides that help extract the light from the microLED projectors. It's really interesting to see how we started, and it'll be great to see how these evolve over time as these projectors get brighter, more efficient, and overall more robust than the unfortunate glass crack that we saw in today's waveguide. And so with that, we finished the teardown of the INMO Go. Unfortunately, we had some damage to our waveguide during this teardown, especially with the amount of glue that is laid down by INMO on the sides of the temples closest to the lenses. That means that we have to use a lot of force to actually pry open this component before we can start removing the Phillips head screws that are required to remove the hinges and all of the other components before we have access to our optical module and waveguide. Overall, it's a very promising start to the AR glasses revolution, where these monochrome panels that are capable of millions of nits outside from the projector deliver high brightness through these very lossy waveguides that we have. The overall product design still leaves something to be desired, especially with the overall waveguide structure being way too far up in the eye box to be very effective. It would be very nice to see these waveguides come further down into the eye box, much like we see from the Rokid glasses that are recently being advertised today. That said, that concludes our review of the INMO Go's. Would really love to see some better software experiences, but for the purposes of the hardware, it was impressive to see the amount of light that can be injected into our waveguides from such a slim form factor with relatively low battery life. As always, thanks for watching, and if there's anything that you'd like to see reviewed, leave it down in the comments below. Thank you.